Just want to do a quick shout today to talk about the big controversy between Newton and Einstein in the death match to end everything, no holds barred, fight to the death. Or more accurately, after 200 years, we finally got a little update to the concept of gravity. Let's get into it. The reason I'm bringing this up tonight is because there are some folks out there in the alternative science group who are really concerned about the differences between Newton's law of universal gravitation and Einstein's theory of general relativity. The premise seems to be that because these are different and because of the peculiar ways that they are different, the alternative science crowd has concluded, or would like us to conclude, that therefore gravity doesn't exist at all. Setting aside the logic of that statement in itself, let's take a quick look at what are the differences between Newton and Einstein. Okay, the first thing I want to point out here is these dates right here. General relativity is Einstein's theory that relates to gravity, and it was in 1915 that he first published his results. When did Newton publish? 1687. So over 200 years earlier had Newton written his laws. Einstein came along quite a while later. So that gave us 200 years to discover new things and 200 years to put Isaac Newton's laws to the test. So over 200 years of scientists, generations of scientists had done experiments, they had published papers, they had evaluated and double-checked and verified that Isaac Newton's laws were remarkably good. There were a few little places that they didn't work perfectly. And that is something that Albert Einstein was able to come in and, patch. If we use a software analogy, if we can use a software analogy for a moment, what happened was Isaac Newton released his laws and they worked really, really well. But they had a few small bugs in them. We all used them. The whole planet Earth used these laws, but they were aware of the bugs, and we just sort of avoided those bugs until along came Einstein, and he finally patched the software of gravity and fixed a few of those bugs. Now, to continue with this analogy that it is a software patch, Einstein had to patch the software, but hundreds of years of people had been using it. He couldn't just throw out the old software. The new software had to be backward compatible. So if I can sum up this entire thing, I can end the debate right now. Einstein's laws are backward compatible with Newton's laws. What does that mean? That means anything that Newton had predicted that had been verified by that time must still apply in Einstein's rules. When Einstein released his formula, the Einstein's field equations, right? There's that statement that you see that with the Greek letters in it. There's not even any need to show that. This is a no math. This is a mathless video tonight. Einstein's equations had to be backward compatible with every experiment that had been done in the past 200 years. Why? Because if they weren't, then they were invalidated the day he published them, right? How does this work? Let's remind ourselves how this whole science thing works. We make a guess at what we think our new law might be. We write the equation. We look at that and we make predictions based on that new hypothesis, right? We make a hypothesis. we make predictions, we test those predictions against real-world observations. If they don't match, then our law is wrong, right? This is Feynman's famous lecture. We've all seen it. We love that lecture, right? So on the day in 1915 when Einstein published his general relativity with his field equations, if those equations did not already match the past 200 years of experiments, then the moment he published them, they would have been shot down and people would have said, no, these don't match observations. We've done observations for 200 years and your equations don't work. But that isn't what happened, is it? Because Einstein was completely aware of this. He built his equations on top of what Newton had done. He took what Newton had done and he extended it. He patched it, he corrected it, and he gave us a new form of the equation that not only explained all the observations for the past 200 years, but also managed to fix those little bugs that were in Newton's equations. Without delving into the equations themselves or looking at any of the math or even getting deep into the science or the history of this, let's do a quick little summary chart to compare Newton versus Einstein, just in some of the big heavy hitter categories of gravity. First up, things fall. Heavy things fall. Newton says they do. And in fact, I think we've seen that they do. What does Einstein say? Does Einstein's equation say that heavy things don't fall? Well, of course not. Einstein agrees heavy things should fall. So we've got an agreement there. How about weight and buoyancy? Can Newton's laws of gravitation explain weight and buoyancy, and can they predict the values correctly? Yes, they can. Here on Earth, Newton's equations had been tested thoroughly. They predict both weight and buoyancy with excellent precision. How about Einstein? Is Einstein going to overturn this one? No, of course not. Can't. We all know that weight and buoyancy work correctly under the existing equations. So these new equations must match those results exactly, and they did. How about the orbits of the planets? The orbit of the moon. Newton derived his equations from the orbits of the planets, so in general, he had a pretty good lock on those. With the exception of Mercury, I've got listed down here. We'll come back to Mercury. But Newton's law of universal gravitation explained the orbits of the planets. If Einstein's equations were going to work, they'd better do that as well. And guess what? Boom, another check mark. Einstein's equations work just fine for the orbits of the planets. Okay, here's the big one. Here's the kicker. This is the one that generates the controversy. Newton said that all masses are attracted to all other masses. But what does Einstein have to say about that? We've all heard it. We've heard gravity's not a force. That's right. I hear you in the crowd. Gravity's not a force. Gravity's not a force. But hold on. Okay. Do masses attract each other? What do you say, Einstein? Einstein says yes, masses do attract each other. Now, the mechanism may be something unexpected, but if you put two masses into the equations of Einstein's field equations, you will find those masses will move towards each other. They are attracted to one another. That's how we get orbits. That's how we get weight and buoyancy. That's why heavy things fall. Einstein's equations predict that masses do attract masses. How about that? Well, that brings us to, of course, the most famous experiment of mass attracts mass that we've ever had, the Cavendish experiment. The Cavendish experiment was the first example of this, and we just call it that experiment now, even though we've done it thousands and thousands of times over the years. There's a really great one. Let's do a shout out for Blue Marble Science. Blue Marble has built the most fantastic Cavendish rig I have ever seen. If you have any doubt that mass attracts mass, go and look at some of his videos and see it for yourself. We can certainly confirm that lead attracts lead, and in the future, he's looking to swap out those lead balls. We can watch as he shows us other materials attracting other materials. Or maybe we'll find out they don't. But Newton said they did, Cavendish did the experiment, and he found that they did. How about Einstein? Under Einstein's field equations, will the Cavendish experiment work? Yes, by now you know where I'm going with this. Of course it does. It has to. The Cavendish experiment was first done well after Newton had published his universal law of gravitation. It was in fact based on that law. So if under Einstein it wasn't going to work anymore, how were we going to explain the past 200 years of experiments? Of course not. The past 200 years of experiments were correct. They were true. They were real. And Einstein agreed with that. Where's the big controversy here? How about big G, the concept of the constant, which incidentally Newton himself never referenced, even Cavendish never referenced. We added that later. We have now a big G, which we can back out of Cavendish's experiment and determine what it was. We can interpret Newton's laws to say that it was implied in those laws, and we have measured it. Cavendish was the first official experiment that gave us the data we needed to measure it, even if he didn't actually calculate the value. He did have the data, and we can do the calculations for him. What's it going to be? Is big G, under Newton's laws, going to be the same big G in Einstein's field equations? Drum roll, please. Yes, check again. In fact, if you look at Einstein's field equations, I promise there won't be any math, but if you happen to go and look, you'll see there's a big G, a big capital G right in the equation. And yes, that is Newton's gravitational constant. That's the exact same constant in both equations. It's sitting right there. Okay, now on to the bugs. I mentioned this before, but in Newton's day, it was already known and understood that his laws, Newton's universal law of gravitation, did not correctly predict the precession of Mercury. It was very slightly off. It was super, super close. Don't let anyone fool you about this. It was like really close, but Mercury precessed by the tiniest little amount that did not match Newton's equations. What did Newton have to say? He said, shrug, I don't know, I guess it ain't perfect, right? He said, well, maybe God does that. That's all Newton had for us. And that's what we had to live with for the next 200 years, and then some, until Einstein came along and created his more advanced, much more complicated equation and put Mercury through it. And what did he find? Boom! Einstein patched the code. Einstein corrected the bug, and now the precession of Mercury worked just great. Okay, there's one more here. Newton wasn't really sure what light was made out of, really. You know, that was quite a long time ago. So we'll give him this. Newton had these ideas about what light was made of, and it turns out he wasn't 100% correct about that. But he did predict that light would be bent by gravity. But unfortunately, due to his misunderstanding of what light was and his imperfect law of gravitation, his guess about how much light would be bent was not correct, although he did not ever discover that while he was alive. While Newton was alive, we were unable to test. No one had come up with the technology to figure out a way to test that theory. It wasn't until 1919, after Einstein had published his field equations, that we were able to test once and for all how much does light bend under the influence of gravity, and boom, Einstein had managed to patch that hole as well without even knowing it was there. So what am I saying here? I'm saying, and you can see it in the chart, Einstein's field equations are 100% backward compatible with everything about Newton's laws that worked. Everything about Newton's laws that already worked must continue to work into the future. So any new release of a new law has to be backward compatible with those things. However, there were a few known and now some unknown bugs in Newton's laws that were not perfect, and that's where Einstein has the opportunity to fill those in and make for us a nice little update in our software package, a nice little improvement to the law. Okay, so that is what the difference is. It's 100% backward compatible with everything that worked, and that means if you want to use Einstein's rules, Einstein's field equations as an excuse to throw out the Cavendish experiment, I'm sorry, but no, it does not work that way. Einstein's equations say that the Cavendish experiment should work. Our real-world examples show that the Cavendish experiment does work. What it really comes down to is this big question right up there. Is gravity a force or not? Newton said gravity is a force of masses attracting other masses. Masses they feel a force of attraction between them. Einstein said something about bent space-time and it's not a force, right? Honestly, for most of us, that's all we're ever going to get. All we're going to get is that it's something about space-time is bending, whatever that means, and gravity is not a force, right? You hear these things. You hear gravity is not a force. What does that even mean? This is a question of semantics. This is not a question of logic. This is not a question of science. This is not a question of mathematics. This is a question of pure, unadulterated semantics. It's wordplay, nothing more. If you actually understand the field equations, we can discuss the mathematics. If you actually follow the science, we could discuss the science. If you looked at my chart on the previous slide, we could talk about logic. The logic says whatever worked under Newton continues to work under Einstein, whether we call it a force or we don't call it a force, right? Mathematics works whether you call it a force or you don't call it a force. The science all works. The Cavendish experiment works. Orbits work whether we call it a force or we don't call it a force. You see, nature doesn't care what words we use to describe it. And that is the source of the confusion. The entire source of this whole confusion is when somebody told you that gravity is not a force under Einstein. Now, what that sounds like versus what that actually means can be two very different things. And that is what we're talking about right now. Remember, Einstein's field equations are 100% backward compatible with Newton. And now, I know you're out there, if you're still even watching, you're shouting back at me, no way, you can't be backward compatible if you say it's not a force. It's just a word. The word force is just a word. Changing the word to a different word does not change the meaning. It does not change the mathematics. It does not change the science. It does not change the logic. You are merely getting stuck on a word, right? Words have different definitions to different people in different contexts. I can hear you right now. I can hear you shouting back at me, words have meanings. The meanings matter. Okay, once you're done shouting, as soon as you're done shouting, wrap that up. Words do have meanings. And it is the meanings that matter, not the words. The words don't matter. It is the meanings that matter. If I understand what you mean, we can communicate, whether you use the correct words or not. English is really the only language I speak, and let me tell you, in English, words have multiple definitions. And if you don't know which one I mean, we can get very confused. Without delving into any of the mathematics, without getting in any of the science, any of the history, even talking about the logic, let's just lay it out right here. Einstein's field equations are backward compatible with Newton's law of universal gravitation. Let's check a few things. Does Einstein say that heavy things don't fall? Of course not. That would be a foolish, ridiculous thing to say. We cannot have built the past 100 years of science on a theory that says that heavy things don't fall. Heavy things do fall. Does Einstein say masses don't attract each other? No, he never said that. That is not what Einstein is saying. You will sometimes hear people, sometimes there are people of actual science background with real science qualifications that will tell you that no, Einstein says that masses don't attract masses. Again, you're getting tripped into the semantics. They are not telling you that the Cavendish experiment won't work here on Earth. They are not saying that. They are not saying that orbits don't happen. They are not saying that at all. What they are saying is that they have another way of looking at the situation in which they describe things differently. And if you haven't made that journey into where you're describing things the way they would like to describe things, you're going to have a communication difficulty, and that is all this is. What does it mean to be a force or not to be a force? What do we mean when we say that? In this case, what we're talking about is that in four-dimensional space-time, we can interpret gravity as an inertial force or a pseudo-force. Now, let me ask you this. Is an inertial force a force or is it not a force? Again, it's a question of semantics. As myself being an engineer, I see inertial forces as a subset of forces. It's right there in the word. It's an inertial, what is it? Inertial force. That's right. It's a pseudo force. That's right. So it's a kind of a force. Now, do I understand when a physicist says to me, no, a pseudo force is not a force. It's like a force, but it's not a force. Yeah, sure, I understand. It's semantics. This is a question of semantics. I would like to treat it as a force. Why? Because my equations that I'm going to use present it as if it were a force. You want to call it not a force? Well, I have seen your equations as well. And in your equations, which work very well, in your equations, it shows that it is an inertial force. I just said that was a force. You want to say that's not a force? That's fine. It's an inertial force. We both understand. As long as we understand each other and we don't get tripped up over the semantics, we can communicate just fine, which is why engineers and scientists use the language of mathematics to communicate. In the language of mathematics, it doesn't matter what you call it. The equation is there and it describes the nature of the behavior. And no one's going to get confused over what is and what is not a force. Einstein taught us a way to think about gravity in a new way, different from how it was thought of before. It's not incompatible. It is backward compatible. It works the same. All the equations still work, and they must work. In fact, mathematically, if you're a graduate student in physics, you will have done this. You will have taken Einstein's field equations, taken the equation that Einstein published, and then you simply plug in velocity equals 0, plug that in there, and then plug in there mass is assumed to be relatively small. Do that, do those two simplifications of the equation, and then solve it out. And what will you find? You will find the whole thing reduces down to Newton's equations. Newton's equations are equal to Einstein's equations if you make those two small concessions. Velocity must be very, very small, and mass must be relatively small. If those things are true, you get Newton's equations, because that's what they are. They're a simplification of the truth. And guess what? We already know Einstein's field equations are not complete either. Einstein's equations are a simplification of the real world. We don't know what the correct form is. We're searching for that. And someday, hopefully less than 200 years from now, we will discover something even better that will take us, hopefully, into an equally powerful leap forward in understanding of the workings of the universe.